Okay, hello. I'm going to talk about fire smoke modeling, and in particular, as the title says, the importance of using a suitable tool. My presentation, I'm going to show you an introduction of the paper and a review of the most common modeling tools available. Some example of good practice, example of problem solved, and then verification of this study that as our file we have done in the last few years, and then conclusions. Introduction. What can I say? We have talked quite a lot about fire smoke modeling, and it's definitely a powerful tool. So you have lots of tools for fire and smoke modeling, and you can use this for performance analysis in fire engineering community. And you can predict the flame height, you can predict the smoke movement, you can predict almost everything if you want, or if you can. So fire smoke modeling is becoming an important part of fire safety engineering. And this can vary from hand calculation to advanced computer simulation. What is really important to understand is which model do what, and which one is suitable for the specific design purpose. And it's also really important to have knowledge and understanding of the limitation of each model. And also, as we are an industry, it's really important to understand, for example, the computational resources you have available, the time limitation, the required level of accuracy, and so on. Modeling tools. This scheme is actually taken from a draft paper that is developed by SFP about validation, and well, it's more an overview of the existing modeling tools and how these models should be used in the fire engineering. So we divide the modeling into three different areas: algebraic models that are based on empirical formula or based on fundamental physics. Then there are some models that, as you certainly know, divide the space into different zones. It can be 2 zones, it can be 3 zones, and in each zone the conditions like temperature, pressure, and mass are uniform. And then at the end there are the CFD models. The CFD model, they numerically solve the Navier-Stokes equation in mean control volumes, and are more useful for complex spaces like very large enclosures, for example, when the limits of zone model can be exceeded. We start looking at these different models, so algebraic, zone, and CFD. And I'm going to show you some examples. They are just examples, a simple example of problems and solutions, or potential solutions. So this is an example of a shopping mall in which you have this long corridor with, full of occupants, for example, and potentially you can have a fire into the shops. And the objective of this study, for example, because you need to size the corridor, no? So you have to propose a recommended width of the corridor. And this can be done estimating when a thermal condition occurred to radiation by fire into the shops. So in this particular problem, how can I solve this? How can I estimate the radiation that comes to the corridor and onto the occupants? This problem, for example, can be solved with the configuration factor equation. I don't want to go into detail of the formulas, but this is an example of how can I calculate this. So estimating, for example, a maximum thermal condition of 2.5 kilowatt per square meter of radiated heat, based on the dimension of the radiation source and the distance of the receptor, I can estimate this value, and consequently the size, the potential size of the corridor. And then next steps in complexity is the zone model. And I'm going to show you another example. Imagine, for example, if you have a quite small enclosure in which you have natural ventilation on the top, And what you need to estimate is just the smoke layer height and the average smoke layer temperature. So in this case, how can I solve the problem? The problem can be solved with a zone model, for example. The compartment will be divided into two uniform layers, a cold one and a hot one, and I can estimate the interface between the cold layer and the hot layer, and I can estimate the average temperature of the hot gases. So, through derivation of equation of mass and energy, I can reach this conclusion, for example. So, achieved with a given network ventilation, a certain layer height and a certain temperature. This can be achieved with software, with the spreadsheet. I can mention, I don't know, CFast, Ozone, Fast, and spreadsheet that you can do with just Excel and put your formula on. And then there are CFD models. That is definitely the final step in complexity. So you need computational time, you need knowledge, probably more than the one used before. When do you use CFD models? Sometimes the validity of algebraic and zone model can exceed, and particularly on large scale projects, or those whose design push the limit of prescriptive design. So sometimes CFD modeling can be the only way to solve the problem. That's an example. It's a very small enclosure. This is actually a sport arena. We need to address the network smoke control assessment in order to guarantee the safe egress of the occupants at a lower level. We're talking about 80,000 square meters with a potential double spill plume beside the bridge. Objective of this is to keep the smoke layer height above the occupants at a certain temperature. How can I solve the problem? This problem can be solved with a CFD modeling. In this case, this is a project that we have done and was solved with FDS. FDS was actually created and validated for this kind of scenario. So I'm quite sure that with the normal uncertainty that the model has, I can rely on this model. And then another important thing is the verification validation. You have a lot of model, but you need to understand which one serves your particular purpose. What I'm showing here is an example, like the one I showed before. And it's a project done by RFire in the last few years, investigating through large-scale fire tests in tunnels.